Sir, we are live.
Dear session chair, presenters, and all the participants or guests of these sessions. So welcome to this technical paper session 3C of the VLSI Design 2021. The session chair for this session is Professor Nitin Chandrachudhan, Department of Electrical Engineering, IIT Madras. In this session, there are 4 papers to be presented in these sessions. Every paper will get 20 minutes, 15 minutes per presentation, and 5 minutes per question answer. All the attendee or guest can ask questions by typing questions during the presentation on the question and comment box on their viewing screens. It is advisable to actually ask questions during the presentation so that at the end we'll have all the questions in our hand. Once the presenter finishes his or her presentations, we will have question answer session. But the guest can ask questions by typing their questions in the question and comment box on their viewing screen during the presentations. It's advisable to ask questions during the presentations so that we'll have actually set up questions at the end of the presentations. And now let me hand over the session to the session chair, Professor Nitin.
Good morning, everyone, and warm welcome to VLSI D 2021 in a virtual format now for the first time. And today we have, thank you, Professor Sahu, for the introduction. And as Professor Sahu mentioned, we have 4 papers in the session today. 15 minutes will be a pre-recorded presentation, and then we have a little time for question answers. So without further ado, let's start with the first paper. It's session 3C on digital circuits and systems. And the first paper in our session is a hardware accelerator for dual standard deblocking filter, which will be presented by P. Saravanan from PSG College of Technology. Over to you, Mr. Saravanan.
Hello, here is our topic for today's discussion: hardware accelerator for dual standard deblocking filter. Myself Saravanan and my co-authors are Cynthia Priyadarshini, Vignesh Khanna and Vaishnavi. We are from Department of Electronics and Communication Engineering, PSG College of Technology, Coimbatore. H265, also called as HEVC, or High Efficiency Video Coding Standard, and H264, also called as AVC, or Advanced Video Coding Standard, are industry standards for video compression that allows for the recording, compression and distribution of digital video content. Deblocking filters are mainly used in these standards to improve the visual quality and prediction performance by smoothing the sharp edges, that is to reduce the blocking artifacts. The prime objective of our work is to design a novel dual standard deblocking filter architecture in VLSI that can support both AVC and HEVC standards. And the second objective is to propose a novel hybrid filtering order to filter out the edges simultaneously, which in turn reduces the number of clock cycles and improves the throughput of operation. Here is a brief outline of our talk. We'll see the introduction to deblocking filter, existing architectures, our proposed architecture, performance analysis, and conclusion with references. Now I request Cynthia to continue with the presentation. Thank you.
Thank you, Saravanan. Now we will be seeing about AVC decoder and HEVC decoder. In case of AVC decoder, the incoming bit stream is stored in an input buffer which undergoes decoding, quantization as well as the transformation procedure, and then it is given as an input to a deblocking filter where the blocking artifacts introduced during the coding process is reduced. Finally, an output video bit stream is generated. The HEVC decoder working is similar to that of the AVC decoder, but it has some additional advantages like the frame coding structure, where the HEVC frames are referred to as larger coding units, which is further divided into coding units, prediction units, as well as the transform unit. Moving on to the deblocking filter, which is our main focus area, it has some basic steps. The first is the boundary stem calculation, which is mainly used to determine what type of filter need to be used during the entire filtering operation. In case of AVC, it has 5 possible values, 0 to 4. In case of HEVC, it has 3 possible values, 0 to 2. This 4 and 2 indicates strong filtering, 0 indicates no filtering, and the intermediate values in the corresponding standard indicates weak filtering. Moving on to the next step is the filtering decisions. Once the boundary strength is calculated, filtering decisions needs to be made. It is done on the basis of macro block in AVC and coding units in terms of HEVC. Here a thumb rule is horizontal filtering must be followed by vertical filtering. That is, if you see here, vertical edges is filtered first, followed by the horizontal edges. Next, filtering operation is done on the basis of boundary strength, alpha as well as beta. It has like 3 main modes: strong filtering, weak filtering, as well as no filtering. The strong, weak, and no filtering mainly depends on the boundary strength value, which we discussed earlier. Moving on to the literature survey, the first paper, a dual standard deblocking filter is utilized, where both AVC as well as HEVC is incorporated into the architecture along with the hardware reusability concept. Thus, this mainly helps in reducing the number of clock cycle required along with increased execution speed as well as lower power consumption. The next paper also incorporates both AVC and HEVC standards along with this symmetric unified cross unit architecture, which mainly helps in reducing the design complexity as well as lower power consumption. Moving on to the next paper, it mainly incorporates AVC standard, where a novel deblocking architecture is proposed, which helps in reducing the number of clock cycle as well as improving the frequency. In the next paper, it mainly incorporates HEVC standard, where features such as resource sharing, parallel processing, as well as pipelining is mainly utilized to reduce the area as well as to reduce the power consumption. And in case of this paper, AVC standard is utilized using quad parallel edge filter along with pipelining and parallel processing mechanism in order to improve the throughput as well as to reduce the area. Now my co-author Vaishnavi will continue the remaining slides.
Thank you, Sandhya. Here we introduce the proposed architecture of dual standard deblocking filter. There are 3 major units. The input to the memory unit is a 16x16 pixel block. It contains 256 Luma samples and 128 Chroma samples. These pixels are stored in SRAM as blocks of size 128 bits. These blocks are fetched and processed and filtered out by the processing unit based on the control signals from the control unit. The input to the control unit are active high start and configuration. Once the entire 16x16 pixel block is filtered, it is indicated by the done flag. These are the blocks inside the processing unit. First, the parameters required for filtering are calculated. Then, based on the configuration selection flag, filtering decisions are made either for AVC or HEVC. Then, based on the filtering decisions made, one of the filtering operations is performed. These are the 4 control signals from the control unit. If the configuration selection flag is 0, AVC filtering will be performed. If it is 1, HEVC filtering will be performed. If the chroma flag is 0, the input pixels to be processed are of Luma samples, otherwise they are chroma samples. If the horizontal edge flag is 0, the input edge to be processed is a vertical edge and hence horizontal filtering will be done, otherwise vertical filtering will be done. A simultaneous flag indicates the simultaneous operation of the 4 filters. This is the state diagram of the control unit. There are 7 states. The idle state is used to set all the control signals to 0. Only when the start signal is enabled, the control goes to load state where the pixels are stored into SRAM. Then, based on the configuration, the control goes to either AVC1 or HEVC1 state for Luma filtering. Once Luma filtering is completed, the control goes to AVC2 or HEVC2 state if the configuration is maintained same, otherwise the control goes to idle state. Once chroma filtering is also done, the control goes to out state where the done flag is raised. This is the proposed filtering order for AVC filter standard. The L blocks on the left are the left edge blocks and T blocks are the top edge blocks. During the first clock cycle, edge pairs L1, B1 and B2, B3 are filtered. During the second clock cycle, edge pairs B1, B2 and B3, B4 are filtered. During the first 2 clock cycles, only 2 edge pairs are filtered because if we try to process 4 edge pairs, it will lead to data overwrite. Hence, only from the 3rd clock cycle onwards, 4 edge pairs are filtered, 2 vertical edge pairs and 2 horizontal edge pairs. Once luma filtering is done, chroma filtering is also done. In the chroma filtering, edge pairs L5, B17 and edge pairs L7 and B21 are filtered first. The remaining edge pairs are filtered in the following clock cycles. This is the proposed register flow diagram. No operation indicates the filter is disabled for the clock cycles. During the positive edge of the clock, the pixels are fetched from the memory or registered, processed and filtered. Only during the negative edge of the clock, they are written into the temporary register for further processing based on the filtering order. This is continued up to 18 clock cycles. We have used symmetric unified cross unit based HEVC filter order. During the first clock cycle, edge pairs B1, B2 are filtered and edge pairs B3, B4 are filtered. Here also only from the 3rd clock cycle, 4 edge pairs are filtered, 2 horizontal edge pairs and 2 vertical edge pairs. Once luma filtering is completed, chroma filtering is also done. This is the register flow diagram for HEVC filtered standard. During the first clock cycle, edge pairs B1, B2 and B3, B4 are filtered. During the second clock cycle, edge pairs B5, B6 and B7, B8 are filtered. This filtering is continued up to 12 clock cycles. My co-author Vignesh Khanna will continue the remaining slides.
Thank you, Vaishnavi. Here we will see the ASIC performance analysis. We have compared our proposed work with the existing 5 architectures shown in the table. We can find the similarity of 16 cross 16 input block size so that we can very well compare our results with the existing ones. Our design requires 18 and 12 clock cycles for AVC and HEVC respectively. We have used 4 parallel edge filters, and in order to improve the design performance, we have used hybrid filtering order technique. Our design can operate at the maximum frequency of 105 MHz. The obtained throughput is 5833.33 kilo MB per second and 546.875 kilo LCU per second for AVC and HEVC respectively. As we know that there is always trade-off between speed, area and power. Since we have used higher level of parallelism as code, we get higher area and power consumption compared to existing works. The design occupies 194.6K standard cells in SCL 180 nanometer process node by Semiconductor Lab, Chandigarh, which consumes 71.82 milliwatt power. Among these 5 architectures, the first 2 are dual standard supporting filters. Among these 2, Srinivasa Rao's paper consumes less number of clock cycles in UMC 180 nanometer technology, so that we have compared our work with their work. Our design takes 18 and 12 clock cycles, and also there is improvement in throughput. Here we can elaborately find the performance improvement compared to Srinivasa Rao's paper. It is about 30.8% and 14.3% improvement in clock cycle reduction. Thus, reduction in clock cycles favors the increase in throughput. In AVC, it is about 1.52 times higher, and in HEVC, it is 1.22 times higher compared to Srinivasa Rao's paper. The proposed design is synthesized using Cadence Janus tool with SCL 180 nanometer process node. Here we can see the physical layout of the proposed architecture. The center part of the layout is the core, which is surrounded by I/O pads. We have used 8-bit wrapper in order to reduce the I/O counts, which we can see around the core. The physical layout is carried out using Cadence Inverse tool. It occupies 4600 cross 4600 micrometer square area. Also, we have implemented our proposed architecture in Vertex 5 FPGA using Xilinx tool. The resources utilized are 84.38% utilization for slice registers. There is 56.10% utilization for slice LUTs, and there is 75% utilization for block RAMs. As a conclusion, our work proposes a novel architecture for dual standard deblocking filter. This architecture makes use of a novel filtering order technique in order to improve the performance and also supports parallel processing of 4 edges, which improves the speed of the filtering operation by reducing the number of clock cycles. As a proof, the functionality is verified using Xilinx tool, and the proposed architecture is synthesized as well as implemented in Vertex 5 FPGA. The physical implementation of our architecture is also carried out using Cadence Inverse tool. These are the list of references.
So thank you for the presentation. I think now we have time for a few questions, and Mr. Sharavanan, one of the authors of the paper, is available with us. Are there any questions from the audience, Professor Sahu?
Audience, we don't have any questions because I'm checking the audience portal and we're not getting any.
So I just had a couple of questions, if I may. Mr. Sharavanan, you are there? Yeah.
Yes, sir. Yes.
Okay. So, primarily with respect to the ASIC implementation, so it was mentioned that, I mean, of course, I can see that, you have a higher throughput. So that is definitely there. But I was curious why the SEL 180, it was more than 2.5 times, I think, the size of the UMC 180 implementation. Is it because the UMC was more tuned towards a smaller pitch width? Is there any observation on that? Did you try it with any other library, or was it done only with the SEL 180?
We have done with the ACL 180 nanometer only, sir.
Okay.
And the reason for the high area is because of the parallelism in our.
Okay. So you're saying that because you have 4x parallelism versus the 2x over there, that made the difference in the area.
Yes.
Okay. And the parallelism is essentially what gives you the higher throughput, I assume, right?
Yes.
Yeah. And one more question with regard to your the FPGA implementation side of things. So you had some number of block RAMs mentioned over there. So does that mean that in the ASIC implementation you had RAM units, or were they implemented using flip-flops in the ASIC?
In the ASIC, we have tried with flip-flops.
Directly with flip-flops, okay. Okay. And what would you say is the the main novelty that you have in this deblocking filter? Is there so what was it mainly the parallelism that gave rise to the higher throughput that you had over here? Were there any other challenges that you saw there?
Yes, sir. The main novelty in our architecture is related to the filtering order.
Okay.
The parallelism in the filtering order, we were able to reduce the number of clock cycles for filtering the cells. So that is how we were able to achieve the high throughput.
Okay. All right. Thank you, Mr. Sharavanan. Thank you for the presentation.
Thank you, sir.
And Professor Sahu, I think we are more or less on time. Do we load up the next presentation? I think 8:20 is when it's supposed to start.
No, we can start a bit earlier, but we will start maybe. Let me ask one question. So, whenever you're calculating throughput, so have used actually 4 parallel filter instead of 2, and you are getting around something 15% or some 1.5 time higher throughput. So 2 times a higher number of parallel unit, but getting 1.5 times. And we are all doing in hardware. Why it is only 1.5 times?
That's a valid question, sir. We are yet to analyze that part because our frequency is also very marginal increase in the frequency when compared to the existing architecture. So we are still working on it. We are trying to improve the frequency of operation as well by using the parallelism as well as pipelining concepts. So that part is left out and we are ready to explore it.
Okay. So I don't have much questions. Now it is time 8:20. So we can proceed for next presentation maybe.
We'll move on to the next paper. This is paper 3C2, an investigation on inherent robustness of the POSIT data representation. And the presenter today is Dr. Farhad Merchant from RWTH Aachen. So over to you, Dr. Merchant. I think the presentation will be played now. So,
hello everyone, my name is Farhad Merchant. I work at RWTH Aachen University in Germany. I welcome you all to my presentation entitled An Investigation on Inherent Robustness of POSIT Data Representation. This work is done in collaboration with some of my colleagues at UPHF in France. So the basic motivation for this work is that with miniaturization of electronic component, the sensitivity of electronic circuits increase drastically. And this sensitivity can sometimes induce errors called soft errors. And these errors can be sometimes single bit flip or multiple bit flips. And these errors can hinder the normal operation of the system. Now, to address this problem, we thought that of exploring a new data format that is proposed very recently called POSIT arithmetic. So in this work, what we have is we do a robustness analysis of POSIT against IEEE 754 compliant format, and then we propose a methodology for exhaustive analysis, and then at the end we cover a couple of machine learning applications to show the efficacy of the format. Now, coming to some background, POSIT arithmetic was proposed in 2017 by Professor John Gustafsson, who is now expatriated at National University of Singapore. Now, here what you see is two equations. So the upper equation represents a number which is in IEEE 754 format, and the equation below represents the number which is in POSIT format. So in IEEE 754 compliant format, what you have is sign bit, and then you have exponent bit, and then you have fractional part. In case of POSIT, what you have is sign bit, and then you have regime field, and then you have exponent field, and then you have fractional part. Now, what extra you have here is the regime field. And the value of regime field is determined by run length of 0 or run length of 1 for positive and negative. What you can also observe in this graph is that POSIT has tapered accuracy compared to floating point. Now, according to the claims in POSIT arithmetic by Professor John Gustafsson, so let's say if you take a 32-bit POSIT number and if you take 32-bit IEEE 754 compliant number, the POSIT number has higher accuracy, it has higher dynamic range, it has simpler hardware if you perform any conversion operation or any arithmetic operation. Also, POSIT has no notion of subnormal numbers. So the subnormal numbers were proposed in IEEE 754 standard to cover the gap between 0 and underflow. So in case of subnormal numbers, you usually change your implicit bit to 0 and then you right shift your fractional part to represent the number. Now, but in case of POSIT, you don't have this notion. Also, when it comes to Noether number, there is only one representation for Noether number. In case of POSIT, it's called Noether real, and there is only one bit pattern assigned to Noether real, unlike IEEE 754 standard, where the bit patterns are in millions. So there is no wastage of bit patterns in POSIT. In my experience, and also based on some of my previous work, what I have observed is that POSIT usually incurs a bit more hardware than its IEEE 754 compliant counterpart. But one advantage that you have in POSIT is, so let's say if you have 32-bit POSIT addition, and if you have 32-bit floating point addition, the accuracy of 32-bit POSIT addition is higher. And hence, maybe you can replace this 32-bit POSIT adder by a 28-bit adder, and you can have a lower area and lower power, while the accuracy remains probably the same as compared to IEEE 754 number. Now, coming back to our idea of addressing soft error issue in the systems. So let's start with a small example of integers. So let's say if you take this 9-bit integer, which I have taken randomly, the value is 469, and when you have a bit flip there, you get error of 6, and the value goes down to 453. This value can also go up if you have bit flip from 0 to 1 instead of 1 to 0. Now, in case of floating point or fixed point number, what you have is you have a fractional part, and the fractional part usually represents the value after the radix point. Now there, if you have a bit flip here, what you can see is the error of 0.5. Now, considering the fractional part of IEEE 754 compliant number and the fractional part of POSIT number, in the case of POSIT number, usually your fractional part is m plus k, where m is the fractional part, number of bits in the fractional part of IEEE 754 compliant number. So here, what happens here is, so let's say if you have a bit flip in MSB of the fractional part, and if you have bit flip at the same position here, then the weight associated here, so weight associated here with this bit is usually much lower compared to IEEE 754. So for example, if we start from here, and let's say if you get bit flip in the 22nd bit, which is 2 power minus 1, then the weight of that in case of IEEE 754 compliant number would be 0.5, while in case of POSIT, it could be k plus that position, so that would be much lower than 0.5, and hence the error that you incur because of the bit flip is lower in case of POSIT format. Now, in our work, we present a framework which is also made open source, and you can find link in the paper. So here what we do is we have a 32-bit word or 32-bit number that we convert to floating point, IEEE 754 compliant floating point number, and POSIT format, and then we inject bit flips. So we support here, as of now, we support single and double flip bit flips, and then we calculate mean relative error distance. And what we observe is that for single as well as for double bit flips, so what we observe here is that for single bit flip, the error is usually lower in POSIT compared to floating point counterpart. And also when we introduce double bit flip errors or double bit flips, the error that we incur is lower than in IEEE 754 counterparts. We also perform application study on machine learning applications. So we consider two computer vision systems. One is biometric authentication system, and the other one is human action recognition system trained with the respective data sets. For feature extraction phase, we use two methods. One is a statistical method, and another one is wavelet transform based method. What we observe here is that for both the applications or for both the systems, the recognition rates are higher for POSIT when we have single bit flip compared to IEEE 754 compliant numbers. So here what you see in gray is for IEEE compliant format, and what you see in orange is for POSIT format, and what you see in blue is without any bit flip. So to conclude our work, what we showed is that the POSIT arithmetic format demonstrates better robustness compared to its IEEE 754 counterpart. POSIT can be used in mission critical systems over IEEE 754 compliant counterparts, though it might have sometimes higher area, but possibility of using POSIT cannot be denied. We also showed application studies, so we did exhaustive analysis, and also we did machine learning applications. One question that remains is, what if there is a bit flip in the regime field? Then yes, definitely the error is higher than floating point, because regime has more weights compared to what you have in IEEE 754 compliant number in exponent format. So one of the solution could be to make this regime field resilient to bit flips. So with this, I conclude my work, and I welcome if there are any questions. Thank you.
Hello, everyone.
Yeah, and I think we have Dr. Farhad with us for the questions. Thanks for the presentation, Farhad. Are there any questions from the audience, or I had a couple of questions?
No, so we don't have questions from audience.
Okay.
So I have also one question. So let you ask first, then I'll ask.
Okay, yeah, thank you. So I was just wondering, I mean, you have done an experimental evaluation, right? Was there a sort of theoretical analysis, some bounds that you could have set for the errors also? Do you think that is straightforward to do for the POSIT representation?
Am I audible?
Yes, you are. Yeah, go ahead.
Okay, great. Yeah, so to answer your question, actually I tried theoretical analysis, and that's where you have this fractional part plus k theory that I have developed. So I also tried to develop theoretical bounds, but in case of POSITs, what happens is, so the regime field is usually identified by run length of 0 and run length of 1, and that you start from left from MSB. So it's a bit of the sign bit. It's you start from there, and then you calculate run length of 0 or run length of 1, and based on that you set your regime. So you see this in the format, you have this UCID power k, and that's where you get k, value of k. Right now, now deriving error bounds in case of bit flips are not that simple, because then I cannot really consider all the cases, because in the worst case I could have all zeros or all ones, and in that case my number can be really large.
Okay.
Right. So yeah, just to answer your question, so yeah, I think it could be interesting to derive such a bound, but yeah, it's not in the scope of this work, because yeah, we also didn't have enough space to put it in the paper.
And I mean, you have given basically a plot which shows the sort of error as, so what is that? I mean, for the different values, it basically how it varies, right?
Yes, so this is a framework that was developed by my colleague in France in UPHF, and there what we did is we injected bit flips at different positions, so we exhaustively, and what we ensured is that, let's say if we are injecting a bit flip from 5th bit from LSB, then we inject at the same place for float and POSIT both.
Right.
Right, because when you have bit flip, the bit flip is not going to know what format your data is.
Sure.
So yeah, so to answer your question again, so what we did is we developed this framework that allows anyone to experiment with it. And also one thing we noticed is that in case of IEEE 754, many times, so since you have this not a number representation, and you have lots of, I think, millions of bit patterns for that, what happens is that a lot of time your number actually gets to NAND format due to bit flip.
Sure.
Which is something that doesn't happen in case of POSIT, because you have only one representation there. So the probability is much lower.
Right. So, I mean, what happens if you want to go to something like, 64-bit representation? Then do you expect it, the gap to become even more? Is it that POSITs are going to be even better at that range? Or what is the actually, I've been hearing about POSITs, but I'm not really sure where is the right place to use them, basically.
Yeah, so if you go to 64-bit POSIT, then your comparison will also be against 64-bit float, because you're not going to compare it with 32-bit float, because it would be unfair, right? So yeah, so then I think you can expect larger gap, of course, because I think your dynamic range would also change according to the platform. But I think for 64-bit, doing exhaustive study is bit tricky, because at the simulation time, so the plots that you see, right, they are very high resolution plots that we have in the paper, and it takes really long time to first to generate them, and then to plot them is also it takes fair bit of time. And another one comment uh, on your feedback on this POSIT, right? So you said you have heard a lot about it. So if you want, you can refer some of my work. So we have done some hardware implementations. So maybe I can send you some of the
Sure.
papers.
Yeah.
We also did RISC-V integration of POSIT. So if you're interested,
I was
can.
asking more from the point of view that are you seeing adoption of this in actual commercial implementations or applications, or is it still in the research stage very much at this point?
Okay, so we have a paper in ISQED this time, which is titled "Brightening the Optical Flow Through POSIT Arithmetic," which is a bit fancy title. And what we have done there is we have analyzed this optical flow application for POSIT, and it's I would say it's a commercial equivalent of I mean it's a so it's an industry paper basically. So it's the paper is from Bosch.
Okay.
Robert Bosch in Bangalore.
Okay.
So yeah, they're adopting it for some of their trying to adopt it for some of their applications, but unfortunately I cannot disclose them.
Sure. But okay, yeah, Professor Sahu.
Yeah, the same question I have asked, whether it is all theoretical or still some industry applications are coming up with POSIT depends on that question.
Yeah, so
but already you have answered, so there's no
yeah,
issue.
okay, fine.
Another thing is, so what will be the situations when there will be error in actually regime part or exponent part?
Yeah, so that is something that I answered in the last slide, because now if you have error in the regime field, so regime field actually contributes a lot to the dynamic range, right? So if you have error in the regime field, that means you'll incur very high error. But the advantage that you have is, even if you have high error, you will not it will not get you to, let's say, something like not a number or not a real in case of POSIT. Right? So your operation will still continue. So if your system is mission critical, you can still recover from there.
But our main goal is getting actually not solved, because we want a reliable one and error should be less.
Yeah, but I mean, IEEE 754 is also not solving the problem, right? But what we are doing now is we are
so maybe
making the system
theoretical
slightly
analysis will be
better.
much better off. So instead of doing some experiment, maybe theoretical analysis doing for the POSIT numbers, if someone can do that, will be good.
Yeah, sure, we can give it a try.
Okay, thank you.
Yeah, thank you very much.
Is there any no questions from our presenter, other presenter also? Let them chance. So let me see the this login screen. So whether other people have asked any questions or not. So till now we don't have any questions. So okay.
One question. Yeah. So how many attendees do we have? I also asked in the chat, but I didn't get answer.
So from outside we don't know, because we are inside the WebEx.
Oh, okay.
So we need to log into VLSI Design, that main website, then only will.
Okay. Okay, so I'll just leave this.
Total conference attendee was around 800. So
okay. Yeah, so I have another presentation in session 3B, so I'll just switch there if that's okay.
Yeah.
Okay.
Thank you very much. Yeah.
Bye.
Yeah. So we are at 8:39. It's almost time for the third presentation. So I think we can go ahead and get started with that. Dr. Sahu, is that okay? Yeah. So the third presentation today is on a reconfigurable hardware-software co-design platform for lung cancer detection and classification. And this is from the LNM Institute of Information Technology. The presenter is Kusum Lata. And yeah, I think we have the, yeah.
Hello everyone. I'm here to present our paper, Reconfigurable Hardware Software Co-Design Platform for Lung Cancer Detection and Classification. Myself Kusum Lata, and the results which are produced here for this paper are produced by my student Aishpat Sarma. The outline of this paper are as follows, that I would be talking about introduction, then I would be talking about lung cancer detection algorithms, segmentation algorithms, classifications, and then I would be talking about proposed platform design approach, and I would be showing the implementation results, and then I would be concluding the paper. So as all of you would agree with, high performance electronics has fueled the rich emergence of the medical imaging applications that has led to the exponential growth in treatment and diagnostic solutions of various medical problems. High throughput and energy efficient systems are required to enable the development of complex medical imaging applications. Next generation medical imaging platforms will need to improve the medical imaging capabilities and developments to enable efficient image processing, 3D model processing, real-time interpretation, and device inference from scanner interfacing, so as to provide smart medical solutions for constant health monitoring. Now I will be discussing about lung cancer detection algorithms. So segmentation is the most significant and challenging task in the analysis of pulmonary modules from the CT scanned image data. Morphological processing in the segmentation algorithm consists of an opening operation with a circular kernel as shown in this following figure. A circular shaped kernel is actually passed over the acquired image data in a filter similar to the convolution for morphological erosion, which is followed by connected component segmentation to preserve the nodule structure parameters and discard vascular components which were initially disconnected. This figure shows the results of the proposed segmentation approach. Kernel-based filter processing employed for averaging and erosion operation and realization of thresholding operation using comparison logic suggests hardware optimized approach for the segmentation. Also, most of the modern day SoC platforms have on-chip kernel filtering accelerators, which further bolster the hardware implementation of these algorithms. Now I would be talking about the classification algorithms. So intensity, similarity, and the spatial proximity can be employed in order to perform grouping of the pixels. Pixels aggregation in region growing techniques starts with a single point and expands with respect to similar characteristics of the neighboring pixels. Clustering is the region-based techniques, and it involves assigning data points to the clusters or the homogeneous classes, such that items in the same class or the clusters are as similar as possible. In the proposed method, we have used fuzzy C-means clustering algorithms for classifying the regions as spanning and the malignant. This figure shows the implemented classification algorithms. The output image from the segmentation step is given as an input to the FCM clustering scheme, which provides the output in terms of relative position of cluster centroids, cluster density, and the area or the parameter of the region of interest, which we are calling this as ROI marked through the clustering. Further, we use a normalized comparison to segregate the detected nodules among two categories, benign and the malignant. These parameters for the classifications are configurable in software implemented codes, and that can be modified based on the application requirement. Now I would be discussing about the proposed platform design approach. In this work, we have implemented a reconfigurable hardware software co-design for medical imaging by exploring energy reduction techniques at various design stages, that is algorithms, architectures, and the logic design. Algorithms are selected for reduced computational complexity and the memory requirements. Parallel and pipeline architectures enable high throughput, which allows real-time processing, and reconfigurable hardware-software system design performs kernel-based filter operations on the hardware section and pre- and post-processing and the resource-intensive classification on the software section. The complete FPGA accelerator hardware integration with the host PC, where we have implemented the software part of it, and the CT scanner. So that's how it is connected. So hardware and the software is interfaced with the UART, and which I would be discussing in detail now. So the proposed hardware-software co-design processor is implemented something like this. So hardware-software implementation of the defined image processing algorithm majorly consists of pre-processing, detection filter, and the post-processing. So pre-processing block performs image sampling, padding, and the serialization. Image sampling blocks divides bigger images, that is 512 by 512 pixels, into the smaller sample images, 64 by 64. Or 128 by 128. Boundaries of these smaller samples are padded with the zeros in order to reduce the boundary condition error in averaging and erosion filtering techniques. Later, serialization block is used to convert the two-dimensional image to one-dimensional signal, where a 2D image matrix is row by row converted to a one-dimensional signal and sampled accordingly. Pre- and post-processing blocks here acts as the interface between the hardware implemented filter and the software-based classification algorithms. Post-processing takes serial output from the detection filter and converts to two-dimensional signal. Later, image binding block is used to bind the parallel outputs of subsampled images. Now, components of detection filter includes averaging, thresholding, and morphological erosion operations. So as you have seen in the previous slide, that software section performs pre and post image processing, where we talked about subsampling, serialization, and deserialization. And then the classification also is implemented in the software section, that is FCM algorithm. And in the hardware section, segmentation filtering is done, averaging, thresholding, and then the erosion, which is configurable, and rate conversion is done with the UART interface rate conversion. So hardware filter bank, which I have talked about, that average filter, threshold filter, and the morphological filter. So in this, nodule segmentation is done as detection. Then denoising algorithm is used to remove the noise from the input CT image in the average filter. Then global thresholding to separate low or high contrast regions in thresholding filter. Morphological erosion to reduce connected components nodules through morphological filter. And we are assuming here circular or disc-shaped morphological erosion. Segmented output image is used for the classification. So in this image, we can see that output image results from the intermediate stages in this algorithm. This figure shows the averaging filter design with its delay structure. So averaging is performed on 3x3 square-shaped kernel, and the 4-stage added tree and the Xilinx library-based floating point divider is used. Then delay structure with the delay values is actually equal to sampling time, and configurable delay kernel is used for 512 by 512 sample is used for single core, and 128 by 128 sample is used for 16 cores. Then this is the schematic of threshold filter design. Global thresholding is done for low and high contrast separations. Library-based relational operator to compare the pixel intensity. Then configurable 8-bit threshold values used and binary output values that is 0 or 255 is used here. Then this diagram shows the morphological filter design. And in this logical erosion is done with minimum intensity logic performed on 3x3 disk shaped kernel. Logical and operation is performed on binary output from thresholding, and delay structure is used with the delay values that is equivalent to sampling time. And configurable delay kernel here again we have used as 512 by 512 sample for single core and 128 by 128 sample for 16 cores. This is the complete system integration. This leftmost image I already have shown you in one of the slides, and the rightmost one is the complete implementation. So hardware software design platform integration with the host PC and the CT scanner. UART interface for the channel between host PC and the hardware accelerator on the FPGA device is there. Software implementation is done using MATLAB script on the host PC. Classification algorithms and then pre and post processing for the hardware accelerators, and results are seen in the MATLAB GUI. Portable platforms for real-time medical image processing. So these are the implementation results. So this table shows basically the resources used with respect to number of accelerators. So as we can see, the number of slices of LUTs used here with respect to the accelerator cores, and the number of cores used in this table are 1, 2, 4, 8, and 16. And then with respect to that, number of used slice registers and the slice flip-flops. Xilinx Spartan 6 LX45 FPGA board is used with a speed grade 3 low-cost device. FPGA resource utilization is shown here. So control logic LUTs and the memory required flip-flops and the registers get balanced for 1, 2, and 4, 8 that we can see from this figure. And it is 2 times more resources for 1 to 4 core implementation. More logic and the memory is required for the parallel cores. 4 times more resources are there for 1 to 16 core implementation. Some more results are here just to show you the total power consumption with respect to the number of parallel accelerator cores. So this image actually shows the power and energy with respect to the number of parallel accelerator cores. A number of parallel accelerator cores are 1, 2, 4, 8, and 16, and relative power consumption, if we see, is 1 times, then 1.07 times, and for the 16 cores, it is coming as 6.61 times. And the relative energy consumption, if we see here in this table, is for the 16 cores is coming as 0.009 times. So we can see that multi-core and the stream-based processing architecture is there, which gives better energy efficiency. Power consumption is increased 4 times. It is increased from 4 to 8 cores. 6.5 times is increased from 16 cores. Overall energy reduction is there. 4 times reduction is there from 2 cores, and 110 times reduction is there from 16 cores. Now, some more results are there, that is with respect to relative latency and the relative runtime. Multi-core and the stream-based processing architectures, which gives us the better performance. Latency reduction is there, 2 times reduction we can see from this table as well as from the graph. from 2 to 4 cores, and 5 times reduction from 8 to 16 core. Overall runtime reduction is there 4 times from 2 cores and 75 times reduction from 16 cores. We have also done the clinical survey, and for that CT image data was obtained on the patients diagnosed with a non-small cell lung cancer with a mixed stage and history from the Ashley Motive Cancer Center and Research Institution, and the reference for that is given in the list of references. Table shows that this obtained data of malignant nodules of 10 randomly chosen patient data, area and perimeter of the nodules in terms of the number of pixels, and then the relative location is also there between left and right lung. In this, I would like to present the clinical survey analysis for the detected pulmonary nodules with respect to area error and the perimeter error. So nodule area and the perimeter error percentage data is presented here. Multi-core accelerated design compared with a single core design. Here you can see that ability to detect malignant nodules, specifying their size and the shape details, and then the multi-core architecture shows a slight error as a result of boundary occurrence of the nodules. 7% error is there in the nodule area measurement and 5% area in the nodule perimeter measurements. Now I would like to conclude the paper. The development and the implementation of a reconfigurable hardware software co-design platform for the lung cancer detection and the classification is presented in this. Optimized algorithms and the parallel architectures, which gives us the energy efficiency. Pixel streaming based accelerator is designed. Multi-core architecture 1 to 16 accelerator cores are used. Multi-core architecture compared to a single core implementation, which shows us that 10 times improved energy efficiency and 70 times reduced execution time. Reduced onboard memory requirements to 125 KB only, and reconfigurable algorithms and the parallel architectures. Configurable filter design engines are designed in this, and configurable data path based on the resolution requirements are used in this. These are a few list of references which have been referred to while working for this paper.
Thank you, Dr. Kusumlata. Dr. Kusum is available for questions, I think. Mic is on. Yeah. Hello, can you hear us?
Yes, sir.
Yeah.
Am I audible now?
Yes, you are. Yeah. Professor Sahu, any questions from the audience? Otherwise, I had a couple of.
No, I don't have any.
So, Dr. Kusum, I was just one thing that struck me was you said that you went to 16 cores and you got 75x speed up.
Right.
I wasn't sure I understood how that is possible. I mean, I would expect a linear speed up. So 16 cores could give 16x speed up. How do you get more than linear speed up over here?
Actually, we have used parallel core architectures. So with that, we were getting this one. So we have optimized at the different levels. The architecture is different. The complete design, that is system design, is optimized at the algorithm level, architecture level. Everywhere we have optimized it, and we were using parallel architecture for this. So that's
when
where we have seen
16 cores, it is not just that one core is taken and repeated 16 times. You are also making other changes inside the architecture.
Yes. We are doing that.
Okay.
Yes, because objective was to get the energy efficient system completely as a whole.
Okay. And you had indicated that the communication between the PC and the FPGA is over the UART. Is there any other means of communication or only the UART?
Yeah, we have used USB actually. USB.
So how is the image actually sent into the FPGA, over USB or over the UART?
Yes. Over the USB.
USB.
USB,
okay.
Correct.
So the latency of the USB and the speed of the USB is not an issue in terms of the overall speed up, is it?
No, we didn't face that.
Okay.
Right.
Okay. Any other questions, Professor Sahu?
Yeah, I have one question. So what is the input size, image size? So what is the input image size?
512 by 512 pixels.
512 by 512 pixels.
512 by 512. Yes.
That's
So that is
the
the in
image size.
general the
And then it has been reduced internally. When we were doing pre-processing, then it has been reduced depending upon the core used.
Another question is the speed up calculation. It is for only hardware part or it is actually end-to-end system?
It is end-to-end.
End-to-end.
Yes.
So
It is
end-to-end
like
system.
the complete system.
Yeah.
Yes.
So starting from capturing the image and displaying
Yes.
the
Yes.
segmented text.
Correct. Yes.
End-to-end.
Complete result. Yes.
So in general, how much time it takes to actually, means in software solutions, it may be in second, and hardware solution maybe in milliseconds. But from the user prospects, so it will not make any sense to those who are analyzing the image.
Actually, this is like a first work which we have completed, that configuration and then getting this done, and after that, this deep learning algorithms and all that is coming. So parallel architecture which we have been doing here at the hardware level, that now we have purchased the Xilinx 7 series FPGAs also, that is JetBot and all. So now I am asking my students to do this on the latest series FPGAs. So the part which has been done, like we are doing the interfacing with the USBs and all, that hopefully it should be done on the same SoC architecture. So that's where all those issues may not come, which you're pointing out. That's what I'm hoping for.
So let me ask one more question. So using this 512 and 512 5 cross 512 image, so what is the
Yes.
exact time it takes in software? So with MATLAB code, how much time it takes?
I think I need to check into those results, Professor. I may not remember it right now.
So it takes in terms of some minutes or hours.
Execution time it was taking in minutes, Professor.
In minutes, okay.
Yes.
For one image.
Yes, for one image. It was larger image, and I'm saying I'm right now I'm talking about if you talk about complete execution time, then it was taking I think 1 to 2 hours, not in minutes. If you say end to end complete execution, like it takes the images, it does all that pre-processing, post-processing, and it goes through, and then when I see that complete outcome coming, it was coming I think it was around 2 hours or so, with the bigger images.
But image size is very small. If you look at your input image size is 512 cross 512. If you do most of the process, you can do in seconds, not in minutes also.
No, but we are doing on a Spartan 6 FPGAs. It was not giving that high performance. And I'm saying for the single core right now.
But how we are reporting then once end-to-end speed up is actually more than 15x or 16x?
When we did it for the multiple cores, and when we reached to the for the 16 cores, then it was increasing. So as we were increasing the number of cores, we were introducing more and more parallelization, and we were optimizing rest of the things. Then we got that much improvement.
Now improvement as compared to your single core implementations.
Correct. Yes, exactly. Yes.
Not with software.
So actually, we could not get any parallel implementation, something like this. So if you see our paper, we have not shown any comparative results. So similar implementation we have not seen, right? So that's why we really do not know what others are getting.
Okay, thank you. So,
okay, yeah, I think we are in time for the next presentation. Thank you, Dr. Kusum, for the presentation.
Thank you, Professor.
Thank you.
And yeah, we will move on to the last presentation for this session, 3C4. That is transistor sizing based PVT aware low power optimization using Swarm Intelligence. And the presenter is Prasenjit Saha from IIIT Hyderabad.
Hello all. Today I've got the golden opportunity to discuss about my research topic based on transistor sizing based PVT aware low power optimization using the swarm intelligence algorithms. I, Prasenjit Shah, have worked on this topic with Hema Sai, my colleague, under the guidance of Dr. Zia Abbas, my mentor. Now, modern day circuits migrate to lower technology nodes for low power, low area, and high performance designs. Low power dissipation determines several specifications such as battery lifetime in portable devices and many other factors. At nanoscale regimes, the static power becomes comparable to the dynamic power, and the circuits tend to be highly sensitive towards the slightest of PVT variations. Earlier approaches including transistor stacking, applying of minimum leakage vector during the idle states, low power RTL designs, each had their own different shades of unwanted effects such as delay overheads or the need to use extra hardwares, etc. Multiple threshold voltages and algorithm based logic gate sizing such as linear programming and convex optimization followed a circuit centric top down approach. This means that the optimized designs could not be applied to any other circuits apart from the ones that are being used, and the entire process had to be repeated for every as we changed from one circuit to another. One other major problem is that the total number of design variables we were working with would increase proportionately with the number of cells or logic gates in the circuit. Over here, we propose a four-fold process of digital circuit optimization. Firstly, we modify the transistor width and length instead of the threshold voltage, despite the fact that threshold voltage has a greater impact on the leakage delay performances. Some of the reasons for this is that it is much more easier to modify the W and L values as compared to the threshold voltage values. Secondly, some minute changes in the W and L values are not amplified at the leakage delay. Are not amplified to at the leakage and delay specifications. Also, certain ways of changing. Also, the adverse effects of certain processes, such as changing the threshold voltage by altering the gate oxide thickness, which might lead to an increase in the gate leakage current, can be avoided. Next, we verify the performances of our optimized cells. So that they stay within a specific bound even in the presence of PVT variations. We reuse our optimized cells at multiple instances, thereby keeping a check on the total number of design variables we are working with. Then we use the optimized cells finally to replace the nominal sizings in the original circuit, and hence the new circuit which gets made up of with this optimized sizing has a lower leakage. So here we follow a bottom-up cell-centric approach instead of a top-down circuit-centric approach. First, we identify the different categories of cells based on what kinds of cells are present. For example, NAND gate or XOR gate, etc. And also based on the total the number of inputs to the gates. For example, a 2-input NAND gate would be treated differently than a 3-input NAND gate. Next, we calculate the input capacitance of each cell category for the delay calculations at various stages. Then the algorithm optimizes the cell for low power while keeping the propagation delay in bounds for the given load with respect to the nominal sizing. The optimized cell can replace the nominal sizing instance in the same or across multiple circuits wherever it faces a load of less than or equal to the optimization load. Now we try to estimate the input capacitance of a particular cell by measuring the propagation delay induced by the cell as the load to that induced by a known capacitor. According to the figure, if you want to replace this target cell with its equivalent input capacitance, we need to find the delay it induces to a driving unit. Over here it's an inverter, and compare the delays that the C equivalent induces with the same driver. Now the value of the C equivalent that we obtain for this Y inverter driver does not change much if we use a different driver instead. If we use some other circuit as the driving module instead of this inverter as shown. Now this algorithm this algorithm based the algorithm based optimization states that the digital cell is optimized for low power by keeping the maximum or the critical propagation delay in bounds with respect to the nominal sizing. The critical propagation delay are found out by measuring all the delay arcs between all inputs and the output. Each sizing solution generated by the algorithm at each stage of execution is a combination of WL values such that the delays are in bounds both at the nominal and the worst delay PVT corners. Now, SpiderMonkey optimization is a recently developed highly efficient algorithm which outperforms well-known algorithms such as genetic algorithm or simulated annealing or particle swarm optimization, etc., in terms of the quality of the solution generated or the total time or the total execution time required. More detailed analysis has been discussed in the paper mentioned. So this is basically a graphical representation of the perturbations that the algorithm undergoes, how the swarm, how the different solutions generated, how they migrate towards some reference solutions referred to as global and local leaders. A detailed of how this takes place can be found in the papers mentioned. Now, as multiple sizes are generated while execution of the algorithm, we make certain observations. These observations, the observation states that as the leakage decreases, the delay increases. The solution obtained at the end of the algorithm we refer to as the primary solution, and this primary solution would have the lowest leakage among all other sizings generated, but at the cost of a high average delay. Using this solution to replace the critical path cells in the circuit may sometimes lead to the critical path delay overshoot. Hence, a secondary sizing is selected from the intermediate stages of the algorithm based on leakage delay performances solely to be used in the circuit critical path. Now, this logic driver model helps us to identify certain transistors whose sizings, if we control, then we can directly control the input capacitance of the cell. So here we can see this is a representation of a 28 transistor architecture of a full adder circuit. The blue shaded transistors represent its corresponding logic drivers. Now, the secondary solution is filtered out from the multiple solutions generated at the various stages of the algorithm with the help of these mentioned criteria. So our targeted leakage delay performance of the primary and the secondary solutions with respect to the nominal solutions are stated below, and these are the criteria based on which the secondary solution are generated. The equations stated over here are known as the fitness functions. So based on these values generated by these fitness functions, whether a solution is, how good is a solution, that is, the quality of a solution is adjusted based on the values generated by these equations. The inequality condition mentioned below is generally used so as to keep the sizings of the logic driver transistors of a cell within bounds, and hence it helps to control the input capacitance of the cell. Now, circuit optimization is done. Circuit optimization is that once all the optimized cells in the once all the cells are optimized, the nominal sizings are replaced with their primary solutions. If the circuit critical path delay is out of bounds, the primary solutions for the critical path cells are stage-wise replaced with the secondary solutions. Starting from the cell 1 as shown in the figure, step by step, the replacement of primary solutions of cell 2 to 5 happens, and after each replacement the critical path delay is verified. The moment the critical path delay falls within the nominal bounds, this cell replacement stops. So we have considered PVT variations such that we have considered plus minus 10% variation in the supply voltage and certain process parameters. Also, we have considered a wide range of temperature variations and input slew times variations from 10 picoseconds to 15 picoseconds, so that the solutions that come out are robust and tends to restrict the performance deviation within a certain limit. These are some of the process parameters that we have considered. So we can see that not all parameters affect the leakage delay performances equally. The parameters which affect these leakage delay performances more than the others are we refer to them over here as the dominant parameters. So the best solution that is generated at each stage of execution are verified against 20 stratified random samples of these dominant process parameters, so that its robustness is verified before moving on to the next stage. So the PBT variations have been introduced by modifying the model by modifying the PTM model cards for the corresponding technology nodes, and all the simulations here we have done using HSpice. So this figure shows the performance the final. So this figure shows the final solutions, the result for this figure shows the result obtained when the final solutions are tested against 2500 random process value combinations, and a Gaussian analysis of the responses is done within plus minus 3 sigma boundaries. This graph belongs to the 2-input AND gate, and it shows about 30% improvement of the mean of the responses for this cell. Now these are some of the results related to the reduction of the leakage. These represents the two graphs represent the leakage value of cells when they are when they are in nominal sizing, primary sizing, and secondary sizing. The left one corresponds to the nominal PBT corners, whereas the right graph corresponds to the worst case leakage corner. So this is a table that describes the results of optimizing complex circuits as the way we have stated earlier. Notice that the C17 and 74182 circuits, we do not require the use of secondary solutions in it, as because if we use the primary solutions only, the delays are within bounds. All the remaining circuits require need the use of both the primary and secondary sizings. So these are the two tables that states the various sizings generated for 22 nanometer AND2 cell and 45 nanometer full adder cell. This table basically states how good the proposed Spidermonkey optimization performs on various circuits as compared to how other benchmark algorithms perform. So in conclusion, we would like to state that the proposed method shows improved results obtained through modifying the device sizes. However, several important factors such as intra-die variations, interconnect delays, we have not taken into consideration. Also, while optimizing a particular cell, if the cell contains more than 12 variables, then it takes up a lot more time to optimize. Also, the search space size, which is directly proportional to the nominal sizing of the cell, if the more the search space size, the more is the time complexity. So the numerous circuits generated during the execution of the algorithms can be filtered out using suitable conditions and saved, so that we can use these sizings later on like a semi-custom design processes.
Thank you for the presentation. And I think we have Prasenjit Saha online with us. Prasenjit, can you hear us? I think your mic is still on mute.
Prasanjit, can you please switch on your video and unmute yourself?
Yes, am I
Prasanjit.
audible, sir?
Yes,
Am I
you
audible,
are.
sir?
Yes.
Professor Sahu, any questions from the audience? Otherwise, I just
No question from audience.
okay. So, Prasenjit, one thing, as far as I understood, you are basically using the swarm intelligence optimization to change the W and L of the various transistors, correct?
Right, sir.
Yeah. So, did you also do some kind of sensitivity analysis? Which are the transistors that affect the output the most? Is there some way of doing that theoretically, or I mean, do you get that kind of result from your optimization?
Yes, we are live.
Hello, am I audible?
Now you are audible.
Okay, sir. Basically, we want even when we try to do it manually, like for every logic gate or every module, if we try to find out which transistor is becoming like more sensitive or less sensitive, so we could have done it manually, but from the results that we got, it seems that the algorithm like automatically takes care of it. Like we are basically varying all the width and length within a specific boundary, so it automatically finds the correct set of sizings that is suitable for each of the transistor as per the connection in the circuit. So we generally do not need to explicitly do it.
Yeah, I mean, I would actually argue slightly the other way, because one of the problems that is generally noted with regard to approaches like swarm optimization is that you don't get any insight into why something is working well, right? So, which are the transistors that have the maximum impact? If you can understand that, then maybe you could have also gone to a higher level and changed your design in some other way. So that was where I was coming from. I mean, is there some insight that you derive from the final results that you get, which tell you that maybe this was the reason why the algorithm picked up on these, and perhaps some other changes could have been done at a higher level.
Yeah, so basically, there is not much difference. But if we look at any parallel stack of transistors, the changes mostly happen if we have a serial stack of transistors. So generally, what we see that the the transistor that is like the most sensitive, like for example, let us consider the normal Elmore delay model. So the transistors whose resistance value will be present in like the maximum number of times, that gets
that gets sized up as in, so that will have like a lower resistance as compared to the other transistors. So like, but that is like analytical, that we know that already. But the swarm intelligence, we do not need to explicitly define that. I mean, we can define that, so that would introduce much more restrictions on like how the variable values will vary and all.
Right,
But
because I mean, I guess you had mentioned that, when you go to more than 12 nodes or something, then the time becomes very large. So, I mean, you need some way of getting around that. So that's where I was wondering whether
right,
there are any other, clues or
right,
intelligence that can be brought into it. Okay.
right.
Were
Actually,
there
sir,
any sort
like
of completely counterintuitive results, things that you did not expect coming out of the optimization?
um counter, I mean, there has been instances where, like, for example, while we were considering the delay arcs from each of the transistors, so
Yeah.
we were expecting that maybe the farthest transistor would have the maximum of the delay, like the delay value, but the sizing got reduced to such an extent that the average delay of all the arcs became equal to the propagation, like the critical delay. So that again increases everything. So like,
Okay.
that's the thing. So that was the reason that we had to bring in this concept of a secondary sizing. Otherwise, it's just like we start the algorithm, we get a result, and done, the method is done. But
Okay.
since this parameter came into existence, that all the average delay increased to a certain level, such that it overshot the circuit, like the critical path delay with respect to the circuit point of view. That is why we had to bring in this concept of this secondary sizing.
Okay. So, yeah, I think any other questions, Professor Sahu, from you or the audience? I think you're on mute, Professor Sahu.
Yeah, I don't have any questions. So
Okay.
thank Prasenjit.
Yeah, so thank you, Prasenjit, and thanks to all the presenters for going through the presentations and sharing it with us today. And with that, we come to an end to this session, number 3C. And thanks, I would like to thank the technical team for organizing all the streaming and other events, and of course to Professor Sahu for setting this up.
Okay. Thank you, Nitin, for actually chairing the session. So
My
giving
pleasure.
you a virtual token of appreciation for chairing the sessions.
Sure.
And we'll save the moment to your mailing address.
Thank you.
Thank you all the presenters. Thank you all the audience of the session. Thank you all the team members of the technical teams. Now the technical PC is formally concluded. That's it.
Thank you, sir.
Thank you.